I'm Rosie. I'm a professor at Computer Science Department at UC San Diego. Today I wanted to share some of the work from our group of grounding foundation models for physical science. So we know that foundation models are very successful and they can enable very smart agents, but still they can make very silly mistakes. For example, if you ask ChatGPT which weighs more, a pound of water or 3 pounds of air, and then you will say 2 pounds of bricks weighs more than 3 pounds of air. Or if you ask Cloud, if I got to the top floor, which is a street level, how many stories does the building have above the ground? And after launching of reasoning, it will still say that the building have 3 stories total above the ground. So one of the fundamental reasons for this phenomenon is that these models are trained purely based on data, so they are only data-driven methods. They lack a framework of physical reasoning. Simply scaling up the model with more data or more compute is not going to guarantee that these models can produce physically consistent and scientifically valid results. Our research on physics-guided AI seeks to address this fundamental challenge by bringing the best of both worlds from machine learning and physical science. So using very efficient inference techniques and expressive models in deep learning, probabilistic models, we can relax the rigid assumptions in physical science and make much more flexible expression of underlying phenomenon. On the other hand, the rich domain knowledge in different physical science and specialized tools such as differential equations and symmetry provide the guardrails for these machine learning models to generate much more physically meaningful predictions. And the ultimate goal is by intertwining physical principles with deep learning methods, we can develop trustworthy AI for science. So now, at the agentic era, agentic AI equips foundation models with various tools. If we think about physical science, mathematical models and numerical simulations are the most essential tools for scientists. Compared to a lot of the agentic tools people are talking about, such as clicking on a web page or playing video games, these tools in physical sciences are extremely expensive. For example, in climate science, when we run climate models to understand the energy transfer from the ocean to the land to the atmosphere, we discretize the entire Earth and solve partial differential equations, and just a single model run would take 6 months. Similarly, for public health, when we wanted to produce stochastic simulations to understand multi-agent movement patterns and forecast the future progression of disease, generating only 100 rollouts would take about 3 hours. So just have a single reward feedback takes such long time. How can we even build agents that can interact with this kind of tool? So that's one of the big challenges here for physical science. These tools are very expensive to run. And then, in order to run these tools, we also need to know the very specialized domain knowledge because they have very different type of interfaces, API calls, and acronyms. A lot of the generic frontier models don't even understand. Finally, because of the missing physics and the gap between mathematical modeling and experimental data, there's a huge amount of uncertainty in the tools. Even with the exact same initial condition, you will get a completely different outcome, and this type of uncertainty will be further propagated with the internal uncertainty of foundation models. So in our group, we have dedicated a lot of effort in building faster emulators to speed up these complex simulations. For example, we built a state-of-the-art global climate emulator that can speed up climate projection from 6 months to a week. And then this is the first model that can generate stable rollout for 100 years at 6-hour resolution. Furthermore, we help domain scientists in epidemiology build fast emulators for public health that enables 100 rounds from 3 hours to 50 seconds. And now this model is being deployed by CDC to project the future progression of public health. Now with the tools, we need to think about how we can interweave them with scientific agents. even though these faster emulators can speed up simulation, they're still quite expensive to use compared to some of the common tools available. We have to be very careful about how we should use tools for scientific tasks. When we think about scientists solving a problem, we have these tools such as mathematical models or literature search, and we also have years of training that's stored in the memory of scientists. So we only use tools when we don't know the answer or we are uncertain of the answer, and then we try to solve the problem with our internalized knowledge. So what I want to argue here is that when we use tools for scientific agents, we need adaptivity. Here's the results for different benchmark tasks for physical sciences. And of course, like with tool using, we're going to outperform all the frontier models. But what I want to focus on is that if we force the model to always use the tool, then it basically leads the model to be reliant on the tools and not be able to generalize to new tasks. And furthermore, there's extra cost comes with using these very costly tools. So the model basically needs to learn when to use tool and how to use tool. It only when they realize that its internal knowledge is not sufficient to answer some of the tasks, answer some of the questions and solve scientific tasks, then it will start to seek external tools and help its knowledge acquisition. Finally, I want to showcase this project funded by DARPA, which is trying to build a generative foundation model for automated climate science. So here, we're pre-training the model with large amount of multimodal data from both large-scale numerical simulations and rich text data from rich literature in textbooks and research articles. We fine-tune these models for a variety of tasks in climate science and weather science, for example, forecasting, counterfactual inference, and scenario creation. What's important here is that we have to ground these models with physical laws. So the technique that we developed is called reinforcement learning with word feedback. And the word that we're developing is based on our fast emulator that can provide feedback based on laws of physics. We can use the uncertainty to guide how the model reacts and use these tools, and then to fine-tune this model specifically for domain tasks. And here I want to show a demo of how Genie works in action. Hopefully it works. That's okay, I can just narrate this over. So what you're seeing here is, okay, that's fine. What you're seeing here is the demo of Genie. So we're trying to build a multimodal foundation model for hypothesis generation in climate science. And on the left is the visualization of the Earth. And then on the right is a natural language interface that you can interact with the agent. So we select the weather bench, a forecasting benchmark for 14 days ahead forecasting, and we select the time and the location we want to ask. Then we ask the model to analyze the data and plot a linear regression analysis for the average temperature, surface temperature. And then model basically generate code using the agentic approach by integrating our specialized tools such as geolocator, fast emulator, and climate simulations. So then you can see the model can generate this kind of plot by retrieving the data and do the analysis in the backend. Furthermore, we can also examine what the code is being generated underneath so that we can provide a layer of explanation what is happening under the hood for this agent. So we can also locate any point on the globe and ask the specialized questions. For example, if we click on this area and then ask the model to generate a meteorological report for this condition in this region, and then the model will then synthesize the knowledge in the literature and the tools available to generate the following report. Then we know this is accurate because we're grounding the model with the physics that we have, so it's not completely hallucinating, and we can also examine the code that's model generated to look at the outcome. We can also ask the model to do forecasting. There's a lot of forecasting models out there, but then often requires special knowledge to interact with this kind of forecaster. So Genie provides a natural language interface for a system to to basically connecting all these available tools like a forecaster and then produce the outcome also in a natural language format. Okay, so maybe I'll just stop here because I'm running out of time. So I wanted to highlight that at the age of agentic AI, the problems in physical science is really proposing the frontier for AI. There's a lot of interesting challenges the current AI system still cannot solve. And I hope everybody can look at this particular domain and all contribute. At the same time, I think the dream, as many of the speakers have alluded to, is that AI and agentic tools is providing new set of gears for AI scientists. By working side by side, we can enable AI system to be more trustworthy with these physical principles and also use the physical principles to help scientists discover unknown knowledge. Thank you very much. And this is my contact information, and thanks for the funding agencies for supporting this work.